Hello again, students, and welcome back. So today, my goal is proving limit laws. And these are things which you probably remember from Calc 1, Calc 2, which are rules that, if you like, let you avoid epsilon n arguments in their entirety as long as you're just combining known facts by algebra. And, well, in some sense, you know a lot of these already. The point is, let's prove them. And this lecture was intended to take up 2 separate class periods, for both of which I'll be gone, which is annoying, but it is what it is. Hopefully this will serve as a decent replacement. Feel free to email me with whatever questions you have. So, we're going to prove some limit laws. We're pretty good at just walking with limits, so let's see if we can prove some things about them. So let's let an and bn be sequences and c be a real number. Suppose that an converges to a and bn converges to b. So this is just the assumptions I'm going to impose to state all of these results. So first, if a is the constant sequence, which is always c, well, the sequence which is always c should probably converge to c. Right? If a is always equal to c, then yeah, as n gets big, a gets close to c, it never goes away from c. If an gets close to a and bn gets close to b, then an plus bn, well, if an gets close to a and bn gets close to b, you're taking something close to a and adding it to something close to b. That should be close to a plus b. If you take a sequence and multiply it by a constant, that should converge to that constant times an. Nope. Times the limit of an. Maybe as long as I just made that mistake. So if you ever find yourself concluding something that looks like limit of an is equal to some other sequence bn, you've just written something that's nonsense. A sequence can't converge to a sequence. A sequence can only converge to a number, or fail to converge. If you take 2 sequences and multiply them together, then the limit is easy to take. It's just the product of the limits. an divided by bn, that should converge to a divided by b, as long as you never accidentally divide by 0. So b had better not be 0 because I'm dividing by b, and bn had better not be 0 because I'm dividing by bn. And as long as you don't divide by 0, then you get the division limit law. Oh, I guess, well, this is technically true, but that is something which I intended to remove from these notes before printing. So, if this were in class, I would go through definitely not all of them because they add up to taking a while, but I'm going to go ahead and do it. I'll bond through it at a decent clip. So let's suppose that an equal to c is a constant sequence. So remember what convergence means. I need to show that for every epsilon bigger than 0, there exists some big N such that for all little n bigger than big N, absolute value of a sub n minus c is less than epsilon. And as per usual, let's consider any epsilon bigger than 0. Let's let big N be, well, we'll figure that out later. We'll consider any little n bigger than big N, then an minus c. Let's just expand that out with the goal that it's less than epsilon. Let's see, an is equal to c, so that's the absolute value of c minus c. C minus c is 0, and absolute value is 0. Epsilon is bigger than 0. Yeah, 0 is less than epsilon. Cool, so we're done. An minus c is less than epsilon. The only shortcoming is, like, this n needs to be picked. You need to demonstrate there exists some n. We never actually use the assumption that little n is bigger than big N, so let's just throw a number down. It doesn't matter what it is. So what have we demonstrated? We've demonstrated that for every epsilon bigger than 0, there exists a big N, namely n equals 1, not that that choice actually mattered, such that if little n is bigger than big N, then the absolute value of an minus c, which is 0, is less than epsilon. So that means the limit of an is equal to c. Cool, done. That's like the easiest one. Let's prove the summation law. So let's assume that an converges to a and bn converges to b. We have to show that an plus bn converges to a plus b. And let's look at these 2 assumptions. We get those 2 assumptions. And we need to use them. So with a lot of proofs where you're proving something about a limit, but you don't have any sort of formula for the sequences you're walking with, you're not going to be able to explicitly demonstrate a choice of big N. Instead, you'll have to use the assumptions to get it. But these, give you an assumption. Since this epsilon is bigger than 0 and an converges to a, there's some choice of big N, I'll call it big N1, such that if little n is bigger than big N, then an minus a is less than, well, shoot. I can put any positive number I want there. Epsilon's a positive number that seems relevant to the question. Maybe you already know that that's not going to walk out, but I'll pretend that I don't. I won't even pretend. I don't know that that won't walk. Similarly, Bn converges to B, so there's some big N2 such that if little n is bigger than big N2, then absolute value of Bn minus B is less than epsilon. So if we let big N be the max between both of those big N's, and take any little n bigger than that choice of big N, well then, since little n is bigger than big N, which is bigger than or equal to big N1, an minus a in absolute value is less than epsilon. Bn minus b in absolute value is less than epsilon. So, an plus bn minus a plus b, that's the thing we want to be less than epsilon. Let's see, by just rearranging terms, that's the same thing as an minus a plus bn minus b, which is good, because this I already know is small. This I already know is small. Right, they're both less than epsilon. They're both as small as I could possibly want. So that means I'm set up to use the triangle inequality. The triangle inequality, if you like, is the thing that says a small thing plus a small thing is a small thing. So that's less than or equal to the absolute value of an minus a, which is small, plus the absolute value of bn minus b, which is small, which is strictly less than epsilon plus epsilon. Well, but I guess here the logic kind of falls apart. Is that equal to epsilon? No, it's equal to 2 epsilon, which is a problem. So how do you fix this problem? Well, in the exact same way as we fixed that last proof from the previous note packet. This can be any positive number I want. That can be any positive number I want. So I need 2 positive numbers, which add up to epsilon, and apparently that's all I need. So think of 2 positive numbers that add up to epsilon. No, not those 2. Let's take the simplest 2. Epsilon over 2 and epsilon over 2. So, let's divide all of the epsilons by 2, and we'll read back through this proof to see if it actually makes sense, but I've just gone through and divided all the epsilons by 2. I've replaced every epsilon by epsilon over 2. Let's see if it works now. So let's assume an converges to a and bn converges to b. I need to show that an plus bn converges to a plus b, so let's consider any epsilon bigger than 0. Grammatically, there should be a full stop there. Well, since an converges to a, there exists some big N such that for every little n bigger than big N, big N1, absolute value of an minus a is less than any fixed positive number. And epsilon over 2 is positive, so yeah, such a big N1 exists. Similarly, bn converges to b, so there exists some big N2 such that if little n is bigger than big N2, then absolute value of bn minus b is less than epsilon over 2. Great, cool. Now, if we let big N be the max between both of those big N's, and take any little n bigger than that big N, well then an minus a is less than epsilon over 2 because of this line. Absolute value of bn minus b is less than epsilon over 2 because of this line. By the triangle inequality now, absolute value of an plus bn minus a plus b, parentheses are important. That's the same thing as an minus a plus bn minus b, still in absolute values, is less than or equal to an minus a in absolute value plus bn minus b in absolute value by the triangle inequality. This is less than epsilon over 2, that's less than epsilon over 2, so the whole thing is less than epsilon over 2 plus epsilon over 2. Yeah, that's equal to epsilon. And so, well, you guys have the privilege of pausing, so I'm going to move to the other page, and if you want to stare at this for a little bit longer, you can pause. So what have we shown? Well, we started by considering any epsilon bigger than 0. So we've shown that for every epsilon bigger than 0, we came up with a big N. So there exists some big N. We considered any little n bigger than big N. So we know that something is true for every little n bigger than big N. And in fact, what did we show is true? We showed that absolute value of an minus plus bn minus a plus b is less than epsilon. Well, that's exactly the definition of an plus bn converges to a plus b. Nice. So there's this result down, and this result down. This result is, in fact, really super easy, and if you want to get it the hardest way possible, it's a consequence of this multiplication law. So I'm just going to prove this general multiplication law. Could you actually see that? I think you could. So proof of not claim 3, this is claim 4. So this one is hard by a little bit, in that there will be a few steps. And I think there are even enough steps that I'm going to find a piece of scratch paper that I can safely write on, and write on that. That's not it. This will do. So this, if you like, is the scratch walk. And I don't need to spell correctly. This is just scratch walk. So I want to show an times bn converges to a times b. So I'm going to start down here. So I'm going to put up here the things that all need to be true about an and bn separately. And now let's measure the distance between an times bn and a times b. And when you look at this and you say, well, I don't know, like, this looks an awful lot like I'd want to factor out an a. I don't know. Sure. Or maybe it looks an awful lot like I could factor out a b, but you can't, right? Bn isn't literally equal to b, it's just really close to b. So let's rig it so you can do that bit of factoring. So let's do it. So let's try to make it so we can factor. And how will we do it? Well, we'll add and subtract something. That's the same thing as an times bn. And I just want to look at my notes to see that I do the same thing, yeah. Let's subtract an times b and add an times b, and then subtract a times b. And right, there are always two questions: can you do something and should you do something? It's clear that you can do this. I've added and subtracted the same thing. The question of should you do this, well, will come out in the pudding. If this actually simplifies down to something we can walk with, then it was a good idea. So let's proceed. So now I can factor an an out of these two terms, absolute value of an times bn minus b. And remember, this is just scratch walk, so I'm probably putting more detail here than I generally would, especially since this is, as I said, scratch walk. Plus, these ones I can factor a b out of, an minus a times b. Now I can use the triangle inequality and even do some more factoring. So that's less than or equal to an times the absolute value of bn minus b plus the absolute value of an minus a times the absolute value of b. Cool, so let's see. Both of those I can make as small as I could possibly want. So both of those I could get less than any positive number I want. I don't know what that positive number is yet, so I'll put a stand-in symbol. I'll put a star there. Alright, so what do I mean by that? I mean there exists some big n such for a little n bigger than big N. Both of those are less than any positive number you choose. So I don't know what I want to choose yet, so I'm putting a stand-in in place. This will be less than, apparently, absolute value of an plus absolute value of b times this mysterious number star that I don't know what it is. So some of you might be thinking, well, right, the end game is, right, set this equal to epsilon, so I'm going to do something that'll be a mistake. Set that equal to epsilon, and that'll tell us what star is. Okay, but there's a problem here, right? All right, so what is the phrasing of limits? So what's the problem with this? So this is definitely not something which would generally go in Scratchbook, but it's such an easy mistake to make if you're not thinking carefully that I figure I'll say it explicitly. The problem here, so look at the phrasing of this. For every epsilon bigger than 0, there exists some big N, definition of limit. There exists some big N such that for all little n bigger than big N, absolute value of a sub n, well, an already has a job. Xn minus L is less than epsilon. So I do get to pick this epsilon. It can be any positive number I want. But it can't depend on big N, because I choose big N after it. And it can't depend on little n, because I declare little n after it. So this thing, it can be whatever you want, but it can't depend on big N or little n. But this depends on little n. So that's a problem. So that's no good. But let's check it out. It depends on little n because of that a sub n. But a sub n converges. That a sub n should get like as close as we want to a. So let's see. I'm pretty sure that I can arrange that a sub n gets as close as I want to a. So I should be able to arrange that, I don't know, a sub n minus a is less than, I don't know, any positive number that you might want to eat. Don't care, 1. Absolute value of a sub n minus a, that is less than 1. Well, if that's true, so that's like the distance from a sub n to a should be less than 1. Let's take that and try to figure out how big a sub n might be. And I can think of 2 good strategies. Maybe I'll use the highfalutinous one and the more intuitive one, because they're both of value. Let's look at rules that govern inequalities. No, I think that, no, let's just do it this way. So what will this imply? This will imply negative 1 is less than an minus a is less than 1. So what does that mean? That means a minus 1 is less than an is less than a plus 1. So an is somewhere between a minus 1 and a plus 1. I mean, I know the result I want, the eventual result. Well, I have notes. No, scratch all that. So let's just try to control an explicitly. Absolute value of an, that's the same thing as an minus a, which I can control perfectly, plus a, which I can control perfectly. It's a constant. That's now less than or equal to absolute value of an minus a plus absolute a. Hey, that's less than 1 plus a. So let's impose this. Let's take this rule and apply that. So remember, this is just scratch walk. I would never want to see you like doing crap like this, like writing arrows around on your final submission. But this is just my scratch walk. So that's less than 1 plus absolute a, to replace that absolute an, plus absolute b times mysterious number star. Aha! But now let's see. If I set that equal to epsilon and solve for star, I'll get star equal to epsilon divided by 1 plus absolute a plus absolute b. There are no more n's there. this is now a reasonable thing to put in place of this star. So I now know everything that I think I should need. So let's look at all of the bounds that I need to handle this. So it looks like I'll need to eventually get absolute value of a sub n minus a less than 1, absolute value of a sub n minus a less than epsilon divided by 1 plus absolute a plus absolute b, and absolute value of bn minus b less than epsilon over 1 plus absolute a times plus absolute b. And that'll do the job. So now we know everything we need. So as you walk through this scratch walk, hold on to it. I don't have enough projection space to project both. So let's just do this. So now we can actually do the proof. Let a sub n and b sub n be convergent sequences. Assume a sub n converges to a, b sub n converges to b. Consider any epsilon bigger than 0. Right, the standard startup that you should have for any limiting proof. Now let's use everything we know. So the first thing I'll do is I'll do this step where I concluded that absolute value of a sub n is less than 1. That'll be like my first goal. So since a sub n converges to a, there exists a first choice of big N1, such that if little n is bigger than big N1, then absolute value of a sub n minus a is less than 1. And this one could be any positive number you want, if you prefer a number like 17, or, I don't know, absolute value of a over 2, or absolute value of a, I don't care. Pick your favorite. So by the triangle inequality, we conclude that absolute value of an, well, it's the same thing as absolute value of an minus a plus a, is less than or equal to absolute value of a sub n minus a plus absolute a, and that's less than 1 plus absolute a. And let's go ahead and number this. I'll call this, no, Star had a job in the notes, which, although they're completely disconnected from this, I'll call this inequality, this step, triangle. Similarly, a sub n converges to a, so there exists some big N2 such that if little n is bigger than big N2, then absolute value of a sub n minus a is less than epsilon divided by absolute a plus absolute b plus 1. Since b sub n converges to b, there exists some big N3 such that if little n is bigger than big N3, then bn minus b is less than epsilon divided by absolute a plus absolute b plus 1. And cool, so just like previous arguments, I have multiple choices of big N. I guess I have 3 of them now. So I'll use the max between a lot of them. So let's take big N to be the max between all of the big N's that we just chose. Consider any little n bigger than big N1, then absolute value of a sub n is less than absolute value of a plus 1. Absolute value of a n minus a is less than epsilon divided by absolute a plus absolute b plus 1. bn minus b is less than epsilon over absolute a plus absolute b plus 1. And maybe I'll remark that if you didn't already know this was going to walk out, those choices all seem super weird. Right? Like, why should those things matter? It's clear that you can do them. Like, we explained how you can get to those conclusions. But they're totally unmotivated, and that's okay. The motivation will come in the second half of the page when we see that things walk out. We'll add and subtract an times b, just like we did in the notes. To get absolute value of an times bn minus absolute value of a times b is the same as an times bn minus an times b plus an times b minus a times b. We'll do some walk and apply the triangle inequality. Maybe I'll do the factoring first. That's the same thing as absolute value of an times bn minus b plus an minus a times b. And the next thing I can do is, you can use the triangle inequality and you can do some factoring to conclude that this is less than absolute value of an times absolute value of bn minus b plus absolute value of an minus a times absolute value of b. Cool, so since an is bigger than big N, I get all 3 of these conclusions. So I get an minus a is less than epsilon divided by absolute a plus absolute b plus 1. bn minus b is less than epsilon divided by absolute a plus absolute b plus 1. And absolute value of an less than absolute value of a plus 1. So now let's just put all this together. So all of this adds up to, so a absolute value of an minus bn is less than or equal to this, is strictly less than absolute an plus 1 times epsilon divided by absolute a plus absolute b plus 1 plus epsilon divided by absolute a plus absolute b plus 1 times absolute b. And by a little bit of algebra, you see that this is equal to just epsilon by simplifying. And that amount of simplification, right, it's all super algorithmic. You factor out. Oh, that should be just an a. You factor out this, and you wind up with epsilon divided by that denominator times absolute value of a plus 1 times plus absolute b. Yeah, so that's just epsilon. So we've now shown that for every epsilon bigger than 0, because we started like the first line of the proof with consider any epsilon bigger than 0. We came up with a choice of big N. It was the max between 3 different choices of big N. We considered any little n bigger than big N and concluded that absolute value of an times bn minus a times b is less than epsilon. Nice. So the proof of 5 is a little bit harder. There is, however, a homework at the end of this which will guide you through the proof completely. So one of the neat tricks that we saw that was useful is as soon as little n is big enough, absolute value of a sub n is bounded above by absolute value of a plus 1. So this is something about like boundedness. The sequence an isn't getting gigantic, it's staying controlled. So this will gain us a useful theorem. Maybe powerful is an overstatement. Every convergent sequence is bounded. Convergent sequences can't grow without bound. But to actually say that theorem, we need a definition. So definition. A sequence of an is bounded above if there exists some number u in R such that for all n in n, a sub n is less than or equal to u. U is called an upper bound. The sequence an is bounded below if there exists an L in the real numbers such that for all n in n, L is less than or equal to an, which, right, is exactly what the definition should be. You already knew what those were going to be. Cool. So next claim. Let me look at time first. Okay. I'm about to hit the 25-minute mark. Well, let me say this. A sequence is bounded if an is bounded above and bounded below. And I'll use this abbreviation a lot, BDD, for bounded, just because I'm lazy. Okay, so I'm going to stop this recording and then begin recording the remainder of this particular set of notes. See you in a moment.